Now I request our second resource person for today's FDP program, Dr. A. Ramesh sir, who is an institute chair professor at IIT Madras. He obtained his PhD in the area of internal combustion engines from IIT Madras and did his postdoctoral research at École Nationale Supérieure d'Athens, France. He has worked in the engine R&D group in Bharat Earth Movers Limited and also as assistant professor in IIT Delhi prior to joining IIT Madras. He has guided several students for their PhD and master's degrees and has published about 200 research papers in journals and conferences. He has successfully completed several sponsored and consultancy projects jointly with automotive industries. Professor Ramesh sir has played a key role in the establishment of automotive laboratories at NCCRD at IIT Madras. Out of more than 21 patents that he has filed and been granted, many are along with automotive industries. Professor Ramesh has received the Srimati Mati Annapurna Gurunath Award for Excellence in Teaching from IIT Madras, Lifetime Achievement Award from SCI India, and the Bhagyalakshmi Krishna Iyengar Award 5 times in IIT Madras. He was also given the Gem of AICTE Award. Several of his BTech, MTech students have won Best Project Awards at IIT Madras and at IIT Delhi. He served as the chairman of Center for Continuing Education at IIT Madras and played an important role in starting the web-enabled MTech programs for industry-sponsored candidates were started. He has been on several expert committees in DST, MNRE, ARAI, CSIR, TIFAC, DRDO, AICTE, ADE, NITs, and IITs. His current research interests includes hybrid electric drives, hot surface ignition engines, JDI engines, RCCI engines, engine control, and innovative engine technologies. It's my pleasure to introduce today's resource person, Ramesh sir. Now I request Ramesh sir to take over the session.
Thank you very much for the introduction. I'll just share my screen. Visible?
Yes, sir. Visible, sir.
Thank you.
Sir.
So, good evening, and thank you very much for providing this opportunity to interact with all the participants. And though it is late in the evening, I'm sure all the participants are quite enthusiastic in attending this session, and I hope I won't disappoint them. Now, the topic that I have chosen here is hydrogen-fueled internal combustion engines for stationary applications. And whatever I'm going to present here is based on our own work at IIT Madras, of course, done by all the PhD and MS students who worked on hydrogen. And so I'm not actually bringing from anywhere else except our own results over the years. And we have been working on hydrogen for about, we started work on hydrogen about 2005, and we were working till about 2015 or so. And this work is basically what was done during that period. So coming to the details of this lecture, initially I'll compare hydrogen with other fuels, because today's lecture is about the use of hydrogen. We're not going to talk about the production of hydrogen, storage of hydrogen and all that. It's only about the use of hydrogen, particularly in engines, different ways in which it can be used. And then we'll look at a few cases, that is a neat hydrogen spark ignition engine, and the use of hydrogen to enhance the combustion of low-grade fuels like biogas, and a neat hydrogen homogeneous charge compression ignition engine, and hydrogen diesel homogeneous charge compression ignition engine, another way of using hydrogen efficiently in an engine. And finally, we'll summarize and conclude. So I was given to understand that this batch of participants are from mechanical engineering mostly, but from different areas of interest. And so I would like to give a brief introduction to engines, particularly related to what we are going to talk, and then we'll go into hydrogen. Now, we know that hydrogen is the simplest of all fuels. And It is abundantly available. Unfortunately, it's not available in the free state. It's available in combination with other elements. So we need to really separate it out and bring it out, and that needs some energy, as we all know. It's a clean burning fuel. It does not produce by itself. It cannot produce any oxides of nitrogen or hydrocarbons or carbon monoxide. So it's a clean burning fuel. Of course, when you burn hydrogen in air, the oxygen in the air can combine with the nitrogen in the air and form oxides of nitrogen. But as a fuel, it doesn't produce anything which is harmful. Then it has got a very high flame speed. That means its combustion rate is extremely high. And this in an engine leads to good thermal efficiency. In an engine, we all know that the combustion has to be rapid for the efficiency to be high. And high flame speed automatically gives rise to good thermal efficiency. Hydrogen also has wide flammability limits, which means that you can use a small amount of hydrogen and a large amount of air. And you can also use a relatively large amount of hydrogen and a relatively smaller amount of air. Still, hydrogen will burn. And which makes it very attractive from the point of view of an engine, because you can now do what is called as qualitative control, like how we control a diesel engine. We don't have to use a throttle. It can also enable burning very lean mixtures. That means a lot of air, less of fuel, which means you have high efficiency because combustion can be complete, and you will also have low levels of emissions, particularly oxides of nitrogen. Other important property of hydrogen is its high diffusivity. That is, it can quickly diffuse into air, so it can diffuse and mix with air very, very fast, which again is very good for an engine because it can diffuse and immediately form a homogeneous mixture. The next property, which is good in some engines and not so useful in some other engines, is the high self-ignition temperature. Hydrogen has a high self-ignition temperature. Is there any background noise that you hear? There are some. Hello? Hello?
Hello, sir.
Is there any background noise disturbance that you're hearing, or it's okay?
No, sir. It is okay, sir.
Okay, fine. Because there are some insects making noise. The high self-ignition temperature of hydrogen can sometimes be useful. For example, if you are talking about a spark ignition engine, high self-ignition temperature is useful. But if you are looking at a compression ignition engine, the high self-ignition temperature does not allow hydrogen to get ignited easily, so that can be a problem. But in a spark ignition engine, it is advantageous. So hydrogen is a very good fuel for a spark ignition engine. And absence of carbon automatically means absence of carbon-based emissions. Now, if you look at the combustion in a spark ignition engine, which is just illustrated by this simple figure, you have a homogeneous mixture of air and fuel. Here it will be air and hydrogen. And you have a spark at almost at the center of the combustion chamber. And then the spark leads to a very high temperature, initiates the combustion reactions, which become exothermic and self-sustaining. And then you have a flame, which moves through the air, radially from the spark, ideally. And this flame is basically a region where the reactions occur. And if the reaction rate can be high, then the flame can propagate fast. So in a hydrogen engine, in a hydrogen air mixture, the flame propagates quickly, and it propagates fast and goes towards the end of the combustion chamber. And on the combustion chamber wall, since the temperature is low, there can be a small amount of fuel which can be left unburnt, and we call this wall quenching. And in a normal gasoline engine, it will lead to hydrocarbon emissions. But in a hydrogen engine, it will of course lead to some hydrogen coming out. And in a normal engine, what happens is the end gas, that is, as this flame is propagating, the surrounding gas gets compressed because the pressures go up, and the surrounding gas also gets heated because of heat transfer and also because of compression. And the surrounding gas air fuel mixture can auto ignite on its own, suddenly ignite on its own even before this flame reaches, and that we call as knocking. In a hydrogen engine, this is less likely to occur because the flame propagates fast and it doesn't allow this to auto ignite. And also this charge does not auto ignite so easily because its self-ignition temperature is high. So this kind of knocking does not occur, but the normal flame propagation itself is like knocking. That itself becomes so fast that combustion can be very rough and it can look like knocking. So hydrogen combustion leads to knocking, but that knocking is not like the gasoline engine knocking. It is just the fast combustion that itself results in knocking. And in a SI engine, you have carbon monoxide and all that, but you don't have this in the hydrogen engine. And high temperature and oxygen in a hydrogen engine can lead to significant levels of NOx. In fact, one of the main problems with the hydrogen engine is the high levels of NOx. The NOx levels can be even about 5 to 8 times higher than what you get in a gasoline engine. Now, the fuel properties that you require for an SI engine are mainly governed by the mixture. The SI engine uses a homogeneous fuel air mixture, so it needs a fuel that can easily mix. Hydrogen is an ideal fuel for this. There's a spark that initiates a flame. You have high combustion rates, which can give high efficiency, and when we can go close to the Otto cycle. Then the combustion rates are associated with fuels which have a high flame speed. That is, high combustion rates means high flame speed. Then the start of combustion is controlled by the spark. The air-fuel ratio or the equivalence ratio is another important parameter, and the charge is normally throttled to control the output of the engine. That is, you normally control the air and the fuel going into the engine to control the output of the engine. But in a hydrogen engine, it is not required, because in a hydrogen engine you can have a wide range of air-fuel ratios. So it's enough to only control the fuel and not control the air. Still, the engine will run. This is a big advantage. And knocking is a problem, and that will limit its performance. And in a gasoline engine, HCCO, NOx are the main problems, but in hydrogen engine, NOx is the significant problem. Now, coming to the CI engine, which is also an engine where you can use hydrogen, you have a central combustion chamber, you have a fuel injector, and you compress only air. And at the end of the compression process, just give me 1 minute, please, 1 second, please. And at the center of the combustion chamber, normally you have a fuel injector, and this fuel injector sprays fuel at a high pressure. The fuel atomizes, mixes with air, then self-ignites. That means the fuel that is required for a diesel engine or a compression engine should have a low self-ignition temperature. And hydrogen has a high self-ignition temperature, so it is certainly not the fuel for a CI engine, but it is used in the CI engine in different ways. And in the CI engine, there is a spray, then fuel droplets, and fuel droplets mix with the air and burn. But that is not the case in the case of a hydrogen CI engine, because you can just not inject hydrogen like this into an engine. So what is the point to note here is that in a CI engine, use of hydrogen directly is not so easy, because hydrogen does not self-ignite, and you have to indirectly use hydrogen in a CI engine unless you are using very, very high compression ratios. So for the fuel, for the CI engine, air alone is inducted and compressed. Fuel is injected at the top dead center, and the fuel needs to have a high C10 number, and the fuel, spray, air motion are all important. And normally in the CI engine, you have smoke and you also have NOx, and this fuel has to have a high reactivity. C10 number is associated with reactivity, and hydrogen does not have a high reactivity. It needs a very high self-ignition temperature to initiate its combustion, but after that it becomes quite fast in the combustion process. So given this, let us now look at the properties of hydrogen and compare them with different fuels. You see here hydrogen being compared with, I'll particularly like to compare hydrogen and natural gas, because natural gas is another fuel which is widely used. So if you look at hydrogen and natural gas, obviously hydrogen is a simple fuel with no hydrocarbons obviously in it. So these hydrocarbons can produce different combinations and produce different emissions, which certainly is not there in hydrogen. The heating value of hydrogen is extremely high. It is 50 for natural gas, megajoules per kg, and it's 120 for hydrogen. That means per kg of hydrogen, you can release very high levels of energy. Unfortunately, its density is extremely low. So the volume of hydrogen that is required to be stored, even for unit mass of hydrogen, is extremely high. So this actually offsets the advantage that you have when you have a high advantage with the high calorific value. So hydrogen actually, in one cylinder of hydrogen, if the conventional cylinder of hydrogen where the gas is stored at about 200 bar, if you buy a normal cylinder, you store very little hydrogen, something like 0.6 to 0.7 kg of hydrogen, that's all, depending on the pressure at which you store, which is insignificant, which is not so significant as compared to how much you can store when it's a gasoline cylinder. So from this point of view, from storage and from transportation, hydrogen has some problems. The flame speed of hydrogen is extremely high. You can see how many times it is higher than in the natural gas. That means combustion can be completed almost instantaneously. This can lead to very high efficiencies, but it can also lead to very high rates of pressure rise and knocking. and the amount of air that 1 kg of hydrogen can take is very large as compared to what natural gas can take. So it needs a very small, it has meant a large amount of air per unit mass of hydrogen. So its stoichiometric air fuel ratio is very high, and its flammability limits are very wide, from 4 to 75 on the volume basis. So even a small amount of hydrogen with a large amount of air can burn. Similarly, a large amount of hydrogen in a relatively small amount of air also can burn. And its octane number, which tells how good a fuel it is for SI engines, is better than natural gas. And its auto ignition temperature is much higher than natural gas. So it is not easy to, even natural gas is not so easy to ignite by self ignition. So these two fuels are not good for the diesel engine, but good for the SI engine. And hydrogen is definitely better than natural gas. Now, if you compare hydrogen and gasoline when it comes to a spark ignition engine, I'll not go to all the properties, most of them are common. If you look at the density, you see the big difference. Hydrogen has a very small density, gasoline being a liquid has a high density. Then the limits of flammability are wide, not so wide. And the ignition energy that is required. This is another important property of hydrogen. The amount of energy that you require to ignite hydrogen is extremely low as compared to gasoline. You can see here that it is significantly lower than that of gasoline. This is an advantage because it can be easily ignited, but it's also a disadvantage, because even a hot spot in the engine would undesirably ignite it and lead to problems of combustion. So this is good and bad. And it is good from the point of view of proper ignition, but it's bad from the point of view of ignition control. So this is another thing. And if you look at the auto ignition temperature, it is significantly higher than gasoline, which is an advantage in a spark ignition engine. And the adiabatic flame temperature is more or less comparable to gasoline. And you can also see that the octane number is extremely high, much higher than gasoline. And another important thing which you see here is the flame quenching distance. That is, it is the minimum gap. Actually, what flame quenching distance indicates is a gap through which the flame cannot pass. That is, a gasoline air mixture flame cannot pass through a gap which is less than 0.2 centimeters. Whereas in the case of hydrogen, it can pass through a gap which is 0.064 centimeters. That means any small gap can also enable hydrogen flame to pass through, which is again not a desirable feature from the point of view of safety. So hydrogen has some safety issues in the like being ignited very easily, being ignited with a wide flame, air fuel ratio range, and having a small flame quenching distance. These are all things which can cause safety concerns. So one has to be careful while using hydrogen. So coming to the important properties of hydrogen, the low ignition energy requirement is an important property. It allows engine operation with lean mixtures without misfire, but it can also lead to some safety issues. The very high flame velocity again enables lean burning and high efficiency, but it can also lead to knock. Its high auto ignition temperature is desirable because it will not lead to any knock in a spark ignition engine. It is desirable from the spark ignition engine point of view, but not desirable from the compression ignition point of view. Another important thing with hydrogen is it is prone to surface ignition. That means any hot spot on the engine can very easily ignite hydrogen. And that can cause pre-ignition, and it can cause ignition which is undesirable. That is again a problem. Its energy density on the mass basis is good, but very low on the volume basis. That means the engine normally leads to lesser power. That means when you mix hydrogen and air, the hydrogen being very low in density, it displaces a lot of air and occupies its volume. So the amount of hydrogen air mixture that goes into the engine does not carry enough energy because air has been displaced. This means that a hydrogen engine will develop lower power than a gasoline engine unless you supercharge or turbocharge it. We also have difficulties in storage and handling, and it is difficult to detect a hydrogen flame because it is colorless, and it has high diffusivity, which is good, good mixture formation, and also from a safety point of view, also it is good. It has low quenching distance, which means that hydrogen flame can pass through even small spaces, which is again a safety concern. So these are the important properties of hydrogen, and these lead to several challenges. First of all, the challenge is in storage and transportation, challenges in augmenting the power of the engine, and not being able to use hydrogen in a compression ignition engine, and not being able to inject hydrogen because it's a gas. It's not so easy to inject a gas into an engine, it is easy to inject a liquid fuel because liquid fuels can be very easily raised in pressure. But gaseous fuels need a lot of work to raise the pressure. Low ignition energy also creates backfiring problems, self-ignition problems through a hotspot, low energy density on the volume basis, probability of leakage because hydrogen is a small molecule, it can easily leak and come out, and it can leak and then burn around the engine, and the user will not know. Hydrogen also can lead to high combustion rates and knocking, and we need to use lean mixtures, and lean mixtures again will give reduced power. So there are some challenges in hydrogen. There are some big attractive features also of hydrogen. Let us see how hydrogen actually behaves on engines by using 3 case studies. I want to stress once again that several safety measures have to be taken when hydrogen is used on an engine. Otherwise, it can be quite dangerous and disastrous. First problem comes because hydrogen flame cannot be detected. We have had instances in the lab where hydrogen was leaking and sometimes it even caught fire and we were not even able to know that it's burning unless we actually use special devices to like thermal imaging and all that to really see whether there is a hydrogen flame. And you need to have what is called as a flame arrestor. That is, hydrogen being such a easily ignitable fuel, the flame can pass through the supply line itself if there is some air and go back to the cylinder and create some problems. So you need to have what is called as a flame arrestor connected to the fuel line to arrest any backfire in case there is some air mixed along with hydrogen unknowingly. Then you need to have, sometimes we need to use 2 flame traps, one which is dry and one which is wet. I'll also show it to you when we show some of the experimental setups. On top of all this, definitely we require hydrogen leak detectors to be used throughout the experiments to trace any leakages. The hydrogen also leaks. I would just want to show you through a picture. If this is an engine and you take hydrogen and you compress, hydrogen can leak from the cylinder, which is above the piston, below into the crankcase and come here. So it could accumulate in the crankcase, and this crankcase, if it is not properly ventilated, then it can explode in the crankcase. And this being a thin metal, it can actually explode. So when using hydrogen in an engine, it is important to ventilate the crankcase continuously. So crankcase has to be ventilated to the atmosphere to prevent explosion by the blow-by gas. We call it blow-by. And if you are using any air measuring system along with this, you have to see that if there is a backflash, that means hydrogen flame can just propagate like this. When the intake valve opens and fresh air fuel mixture is going into the engine, there could be some hot spot which will ignite it even during the suction process, and the flame can go backwards into the intake side, and it can explode somewhere here. So we need to have measures where if there is a pressure buildup, it can simply rupture and not create any problem on the intake side. So such diaphragms have to be fitted. There should also be venting arrangements provided on the hydrogen supply line, because after the engine is run, you need to ventilate the supply line. Of course, crankcase ventilation also is one of them. And then it is always good to do what is called as timed injection of fuel rather than mixing the air and fuel. That means you allow the injection only when the air is going into the engine, so that you don't retain any hydrogen in the intake manifold when the suction is not occurring. So these are some of the precautions that one has to take when using hydrogen in an engine. Now, coming to the methods to use hydrogen in engines, basically there are 3 methods. The first method and the simplest and preferred method is the spark ignition engine. In the spark ignition engine, we have the engine which can operate in the lean burn zone or in the stoichiometric zone. In the hydrogen, we always prefer the lean burn arrangement, where you have a lot of air, less of fuel. And because hydrogen can burn lean, it's easier to work in this mode. And this mode, you can get complete combustion, good efficiency. So one prefers to use lean burn. But when you use lean burn, a lot of air and less of fuel, you automatically end up in lesser power because you are not putting enough fuel. And hydrogen already is on the volume basis, hydrogen's density, energy content is low. So we end up in getting lower power from a normal SI engine as compared to a gasoline engine. So it may be important to supercharge a hydrogen engine when you use in the spark ignition engine mode. The next mode, which is again somewhat popular, is the CI engine mode, where in the normal CI engine, that is compression ignition engine, we already saw that if you compress air alone and try to inject hydrogen into the cylinder. Injection itself is difficult. And even if you are able to inject it, combustion will not occur because hydrogen requires a high temperature for ignition. And that means the air has to be compressed significantly, which is not practically feasible. So hydrogen in the CI engine is not used in the normal form. It is used in what is called as the dual fuel mode. That is, there is a primary fuel and there is a secondary fuel. And our intention may be to use hydrogen as the primary fuel, but there is also what is called as a pilot fuel. So the pilot fuel would be diesel or any renewable vegetable oil or anything which is like diesel. So what we do is we take in air into the engine, compress the air, and along with the air, you also take hydrogen. That means you compress air and hydrogen mixture. And when you compress, it doesn't ignite because hydrogen has a high self-ignition temperature. So we compress the air and hydrogen mixture. And for ignition, like in a normal diesel engine, we inject some diesel. So this diesel goes into this compressed air hydrogen mixture. And this diesel first burns and then ignites the hydrogen. So the diesel acts as a multiple spark plug source, spark source, and then ignites the hydrogen. So this is a very simple arrangement. The engine need not be modified significantly. You just have to add a hydrogen line to the intake manifold or a hydrogen injector to the intake manifold. Along with air, hydrogen goes inside, it's compressed. At the end of compression, diesel is injected or something like diesel is injected and combustion occurs. So this is the so-called dual fuel mode and it has some specific advantages. We'll see that. The third and new method, relatively new method, I won't say new method, relatively new method is the homogeneous charge compression ignition, where we don't use a secondary fuel. We may or may not use a secondary fuel like diesel. And here what the idea is to take a lean mixture of air and hydrogen and compress it and self-ignite it. That means you need to self-ignite. That means you need to make hydrogen to ignite on its own or mix hydrogen and diesel and then get this mixture to ignite on its own. And the overall mixture is very lean. And the main advantage of this method is extremely low levels of NOx can be got. You can get low levels which you can never get in any other engine. And there will be no need for any after treatment at all. Significantly low levels of NOx and no soot, and of course no hydrocarbons and carbon monoxide. So this will be a very clean engine, but the problem is control of combustion and control of the load. So each one of them has some advantages and some problems, as we'll see. But SI engine is the most, easiest method. Now, if you want to compare the CI, SI and HI engine, HCCI engines, the CI engine uses a spray and you compress air and then you inject a spray, and that spray could be any fuel which is which easily self-ignites. Unfortunately, that spray leads to very high temperatures, local temperatures, and high levels of NOx. So one of the problems with the CI engine is high levels of NOx. And another problem with the CI engine is high smoke because it is not well mixed. In an SI engine, you have a flame which is propagating, and in the flame region also temperatures can be very high and you can have NOx. And in the HCCI engine, which is something in between the SI and CI, you have a lean mixture like the CI engine, and you also have auto ignition, but you don't have a spark. So, and you don't have a flame like the spark ignition engine. So it is a lean homogeneous mixture, which is like a homogeneous mixture in the spark ignition engine, but compression ignition like in the compression ignition engine. So the ultimate advantage is that there is no flame here. It is combustion everywhere in the combustion chamber, and you reach very low temperatures during combustion as compared to the other two engines. So you have negligible NOx, and of course, even with fuels like diesel, you have negligible smoke. So these are the advantages of the HCCI, but combustion control is very difficult. Load range is also limited. So let us see how these three fare. So I first take a case which is utilization of hydrogen in a spark ignition engine. So this is a spark ignition engine. So these are some of the experimental results that I'm going to show you, which we did on a spark ignition engine. And this is an automotive engine, a single cylinder automotive engine, but we converted it into a constant speed engine for hydrogen experiments. And so basically what we are looking at is something like a genset application. So what actually happens here is you have a homogeneous mixture of air and hydrogen, which is sucked into the engine. And this hydrogen is actually injected into the intake manifold along with air. So I'll show the schematic. And this injection can be timed manifold injection, or it can be untimed manifold injection. That means you simply keep on injecting into the intake manifold the required amount of hydrogen, or you inject the hydrogen only when the air is going into the engine. So it can be timed or untimed. And the advantage and disadvantage are here. If you have timed manifold injection, it's slightly complicated, but you will not have any hydrogen air mixture left in the engine, in the intake manifold, after it is sucked into the combustion chamber. So there'll be no problem of backlash. But in untimed manifold injection, there'll be a possibility of backlash. Sometimes flame can come back, as I told you. And you need a spark plug which will not become very hot, because I told you that hydrogen will be can be easily self-ignited or easily surface ignited. Sorry, not self-ignited, easily surface ignited. So if a spark plug is hot, it can ignite the hydrogen air mixture even as it is going inside. So you need a low temperature spark plug. So the spark plug of a normal engine has to be replaced. Then you still have pre-ignition problems from some hotspots which you have to control. And since hydrogen has a high self-ignition temperature, the compression ratio of a normal SI engine can be raised without any problem of knocking. And this will also enhance the thermal efficiency. And the intake need not be throttled like a normal engine because hydrogen has wide flammability limits. So these are some of the things that one has to incorporate in a hydrogen SI engine. So this is the figure of the experimental setup that we used. I am specifically showing this to show you the safety devices that are here. First, the hydrogen comes from a cylinder which is kept outside the lab. It comes inside through a water trap. So this is a water trap. So hydrogen is flowing into water, bubbling through water, and then it is coming out. And then it goes into another flame trap, which is a dry flame trap. Hello? Hello? I see some disturbance. Hello? Am I audible?
Yes, sir. Yes, sir. It is muted, sir, now.
Okay. So you have a dry flame trap, which is particularly a mesh through which hydrogen flame cannot pass through. It will be quenched, and the mesh size is less than the quenching distance. And these are two safety devices to prevent any flame from going back to the cylinder if there is some air left into the intake pipe, in these pipes. And then hydrogen goes into the intake manifold. You can see that hydrogen is now injected somewhere here, and it can be inducted into the intake manifold like this, or it can be injected through an injection system, which I'll show you. So this shows the injection system that we used. It's an electronically controlled injection system. So this is the hydrogen injector, and hydrogen injectors are also to be specially procured because the normal seals and all give way with hydrogen. So we have two hydrogen injectors here, and these two hydrogen injectors receive hydrogen under pressure, and you have an electronic controller which is controlling the injection system, just like how you have in modern SI engines. You should remember that this was done some 10, 12, 15 years back. So during that time, these hydrogen injectors were not so common. Even now, hydrogen manifold injectors are available, but hydrogen direct injectors are not available. So it's still not very widely used. So this is injected directly into the intake manifold, very close to the intake valve, so that no hydrogen is accumulated in the intake pipe. Now this shows the schematic: the water flame trap, then the dry flame trap, then the intake system, and then you have the injection circuit and the injection system into the engine, the gas injector, and the exhaust analyzers and the dynamometer and other things. So these are the specifications of the engine. It's a automotive engine, but as I told you, it has been converted to work as a stationary engine. And this engine can run on gasoline basically, but we have now converted to run on hydrogen with its new injection system. So I'll just skip this. So if you look at the results that we get out of this engine, so you can see here that on the x-axis we have equivalence ratio. For those of you who are not familiar with equivalence ratio is the air to fuel ratio that the engine is actually using, fuel to air ratio, mass of fuel by mass of air that the engine is actually using, divided by the mass of fuel to mass of air under stoichiometric conditions. That means if the equivalence ratio is greater than 1, you're using more fuel than the amount of oxygen than what that the air can support. And if it is less than 1, you're using less fuel than what the available air can support. So this is rich mixture. This is lean mixture. Lean in hydrogen, rich in hydrogen. So 1 is exactly correct, chemically correct amount of hydrogen. So you are seeing here equivalence ratio on the x-axis, and you are now comparing gasoline and hydrogen. Let us not worry about this 4 bar, 5 bar. The 4 bar, 5 bar are two injection pressures for hydrogen, and you essentially see that since hydrogen is a highly diffusive gas, the injection pressure does not matter so much. Hydrogen, even at 4 bar, it spreads as easily as at 5 bar. So this is just to show that injection pressure does not affect significantly. But the point to note here is the power that the gasoline engine can produce is higher than the power that the hydrogen engine can produce. And the equivalence ratio to which you can comfortably go with a hydrogen engine is less than what you can use in the gasoline engine. In a gasoline engine, you can even use richer than stoichiometric mixtures. In a hydrogen engine, when you go close to stoichiometric, there is a significant increase in NOx. So you wouldn't want to go very close to stoichiometric. And the engine combustion rate also becomes very high. So we'll see that later. So there is a restriction in the equivalence ratio range, and there is a restriction in the power output with hydrogen. These are some of the one of the observations. And the power anyway has to drop because hydrogen is a gas and it will displace air. This is a well-known thing. And to boost the power, one can supercharge the engine, then the power can be recovered. And the advantage is that there is no hydrocarbon, no carbon monoxide. Now this shows the efficiency of the engine versus brake power. So this is the efficiency of the gasoline engine, and this is the efficiency of the hydrogen engine. So the efficiency of the hydrogen engine is always higher than the efficiency of the gasoline engine, even at the same compression ratio. You can see these two are for hydrogen. And as I told you, with the hydrogen, you can raise the compression ratio because its self-ignition temperature is higher and it will not auto-ignite. So if you raise, you are likely to get higher efficiencies than even what is seen here. So the hydrogen engine is definitely more efficient than a gasoline engine, even without any big modifications. But still higher efficiencies can be reached. Now, if you look at the fuel consumption, the total amount of fuel in kilograms per hour, obviously the hydrogen fuel consumption will be less because its calorific value on the mass basis is higher, much higher. So gasoline in kg per hour is much higher, hydrogen in kg per hour is much lower. This is just because its calorific value on the mass basis is much higher. But if you look at the volume flow rate, gasoline will be significantly lower than the hydrogen's volume flow rate because it's highly dense as compared to hydrogen. But this just shows the mass flow rates. Now, another important feature is the ignition timing. Now, if you look at ignition timing, what is this ignition timing? Ignition timing is the timing at which you have the spark. That is, you take air fuel mixture into the combustion chamber during your suction stroke. Then you compress it. And when the piston is about to reach top dead center, nearly reaching top dead center, you fire the spark. And the spark is fired a few degrees before top dead center. And that is what is the ignition timing, degrees before top dead center. So if I say that it is 15 degrees before top dead center, it means that the spark has occurred 15 degrees before the piston reached top dead center. And why do we ignite it before it reaches top dead center? Because combustion takes some time. Combustion takes a finite time. And if you ignite the spark at TDC, then the combustion may run through the expansion stroke. So you want it to be phased properly around TDC so that combustion will occur close to TDC. So spark timing is always before top dead center. And if the fuel burns slowly, you have to start the spark very early. If the fuel burns fast, you can go close to TDC and then start the spark. So that's what you see here. So with gasoline, you find that the spark has to be significantly advanced. And this high spark advance is required for taking care of the slow burning of gasoline. Whereas with the hydrogen, the spark can be very close to top dead center. In fact, sometimes it's almost at top dead center. When you're using a high amount of hydrogen and small amount of air, and the equivalence ratio is close to stoichiometric, the combustion of hydrogen is very fast. And at that time, you don't have to advance the spark significantly at all. And so there's a wide difference between the spark timing of hydrogen and gasoline. This is one thing which has to be taken care of right at the beginning. We cannot use such timings because then it will, even before the piston reaches top dead center, the combustion will be complete, which will result in very poor efficiency with hydrogen, unless properly it is timed. Now, if you look at the volumetric efficiency, what is volumetric efficiency? Volumetric efficiency is the defines actually how much of air is going into the engine. In a very crude way, if I have to, very simple way, if I have to explain, volumetric efficiency tells how much air goes into the engine in every cycle. And if it is 100, it means that the maximum amount of air per cycle is going into the engine. And you find here that with gasoline, the volumetric efficiency with respect to power was very low, and it goes up like this. The reason why this happens is with gasoline, we are throttling the engine. That is, this WOT is only for hydrogen. With gasoline, we are actually throttling the engine, which means that when you put small amount of fuel for getting small amount of power, you also reduce the air that is going into the engine. Otherwise, the engine will not run, because gasoline does not have a wide flammability limit. If you reduce fuel, you also have to reduce air. And to reduce air, you have to throttle the engine. So this is all with throttling. So low power means low volumetric efficiency. High power means high volumetric efficiency. On the other hand, if you look at hydrogen, we never throttle the air, because hydrogen can run with lean mixtures as well as nearly stoichiometric mixtures or even rich mixtures. So we never throttle the engine. So we allow all the air to go always, and then only allow the hydrogen along with air. So as hydrogen quantities increase, that means power increases, the quantity of hydrogen is increased. We find that air is being displaced. Some of the volume that air has to occupy is now displaced by hydrogen, because hydrogen is occupying that volume. Whereas gasoline has a very high density, it doesn't occupy significant volume. So the amount of air going into the engine keeps on decreasing as we increase the amount of hydrogen. So the volumetric efficiency keeps on falling with hydrogen as we increase the amount of hydrogen. This is something which is different from what we observe in a normal engine. This is because we are not throttling the engine. And this is an advantage actually. But the disadvantage is because hydrogen is displacing too much of air. And this can be compensated by compressing the air and sending it into the engine. That means we can turbocharge or supercharge. So this is another phenomenon that occurs with the hydrogen engine. Volumetric efficiency drops with increase in power because hydrogen displaces air. And this is because of the low density of hydrogen. Whereas in the case of a conventional engine, volumetric efficiency increases because we open the throttle wider and wider as we increase the amount of fuel. This is another difference that we see. Coming to HC emissions, one would expect zero HC emissions with hydrogen because there is no hydrocarbon, there is no carbon in the fuel at all. But you will find that there will be a small amount of HC that is just because of lubricating oil that goes into the engine. The lubricating oil that is on the cylinder liner and all that somehow gets into the combustion process because it's not completely scraped by the piston rings, and some amount of hydrocarbons come out, particularly when the load is very high and the temperatures are high. So this is just by the leaked lubricating oil. Otherwise, hydrogen should not produce any hydrocarbon at all. So if we can develop the engine specifically for hydrogen, this can almost be made zero. Coming to NOx emissions, this is the most significant emission in the case of a hydrogen engine. And you see a drastic difference between the conventional engine and the hydrogen engine. In the conventional engine, you see that the NOx is almost around 1000, 2000 ppm, and generally around 1000 ppm or so on. But if you take a hydrogen engine, it reaches something like 8000 ppm, which means that the NOx levels can be significantly higher in a hydrogen engine. And this peaks very close to stoichiometric, slightly before stoichiometric, about 0.8 equivalence ratio or so, the hydrogen, the NOx level peaks up. The main reason for this is the hydrogen air mixture results in a very high temperature. There are several reasons for this. One is the adiabatic flame temperature of hydrogen. The second is hydrogen is a vapor when hydrogen is a gas as it enters, whereas gasoline is a liquid as it enters, and gasoline picks up latent heat and cools the charge, but hydrogen does not pick up any latent heat and cool the charge. But the most important thing is the high flame temperatures that you experience and the rapid combustion that you experience with hydrogen. The temperatures quickly go up with hydrogen in the engine, and the high temperatures that we reach result in high oxides of nitrogen. So we find that the oxides of nitrogen can be a real problem in the case of hydrogen, unless we go to lean mixtures, where the oxides of nitrogen can be very low. But if we go to lean mixtures, the power output also will be low. So this is a problem with the hydrogen engine. So this problem can be tackled using supercharging. And today engines are supercharged, so this problem can be overcome. So we use a lean mixture, be somewhere here, but supercharge and raise the power. So that's the way to operate a hydrogen engine. Now, comparison with gasoline, this is actually the heat release rate. This shows how hydrogen, the fuel releases heat in the engine. It is joules per degree crank angle. You can call it, this is proportional to joules per second. So it is proportional to watts, let us say. The rate at which the hydrogen is releasing or gasoline is releasing energy into the combustion chamber. You can see hydrogen releases energy like a spike, whereas gasoline burns over a longer period. That means gasoline is slow burning, hydrogen is fast burning, and it is almost sudden. And this sudden burning of hydrogen only raises the temperature and raises the NOx levels significantly. Whereas gasoline is burns over a long period, so temperatures do not go very high, and you find that NOx levels are lower. Whereas with hydrogen, the NOx levels are significantly high. So it is a rapid burning of the fuel that results in high pressures, high temperatures, and high NOx, and also noise if it is not properly controlled. So this is a comparison between hydrogen and gasoline. So the main issue that we have seen so far is NOx. Advantage is thermal efficiency, wide flammability limit. NOx is the main problem, and the other problem is the lower power that you will get from the hydrogen engine. The lower power problem can easily be tackled by using supercharging, so we are not going to look at that. But the higher NOx problem has to be solved using different methods. And so there are some standard methods which can be adopted to control NOx, and we'll see how these actually work on a hydrogen engine. So if you look at NOx control methods, the NOx is actually influenced by the availability of oxygen and the high temperatures that can exist during the combustion process, and the time for which you expose the charge to these high temperatures and oxygen. That is concentration of oxygen. Nitrogen is always there. So concentration of nitrogen is also important, but nitrogen always being there, we don't even talk about it. So concentration of oxygen, temperature, and time. All the three are required for NOx. So NOx is a rate controlled process. So NOx rate is there, and it's not and if you give more time, more NOx will be formed. If you have more temperature, also more NOx will be formed, and higher concentration of oxygen and nitrogen, also higher NOx will be formed. So NOx is influenced by all this, and in a hydrogen engine, there is oxygen because the mixture is normally lean, and temperature is also very high because the combustion is rapid. Only thing is the time of exposure is not very high because combustion is rapid. But then the other two are enough to actually raise the NOx level. So one can think of different methods. One of the methods which SI engine designers very frequently follow is retarding the spark. That means you don't keep the right spark, you slightly retard it. That means if you have to have a spark at 15 degrees before top dead center, you keep it at 10 degrees before top dead center. That is, move it away by about 5 degrees or 6 degrees. So the peak temperature will fall, but there will also be a drop in the thermal efficiency. That means you have to sacrifice efficiency for NOx. This is one of the ways, but it's a simple and easy way to control NOx, and it is also followed. And so this is one method. The other method is to dilute the charge. That is, use some other diluents along with air, so that the temperature can be controlled and the oxygen concentration can be controlled. So the diluents that can be used to control the formation of NOx can control the concentration of oxygen or concentration of nitrogen, but oxygen is the one which is easily controllable because nitrogen is in abundance in the cylinder. And when you use a diluent, it can have different effects. The diluent can just lead to dilution. That means the diluent will simply reduce the concentration of oxygen. That means it can be a diluent, or it can also increase change the thermal characteristics of the charge. That means it can raise the specific heat of the charge, and because the specific heat raises, the temperatures will come down. And it can also have chemical effects. It can also play with the rate of the reaction itself. So it can have all these effects. And so we studied the effect of different diluents. So the added diluent will replace an equivalent amount of air, which will reduce the concentration of oxygen. And the reduction in oxygen concentration will decelerate the chemistry of NOx formation. And diluents can also have specific heat, increase the specific heat of the charge and affect the temperatures. So the probable diluents are carbon dioxide, which has a high thermal effect, nitrogen, which can be and you could also use some other diluents, specific diluents, just for the sake of study, like helium, argon, and water vapor is another diluent because you can easily pump water into the intake manifold. So these are some of the diluents that can be studied, and we studied the effect of carbon dioxide, nitrogen, and also exhaust gas. So dilution by nitrogen is one of the methods which we tried, because if you cool the exhaust gas of a hydrogen engine, it will predominantly contain nitrogen, because once you cool, the water will get condensed. The output of a hydrogen engine is water vapor, and some excess oxygen may come out, and nitrogen will definitely be there. So if you cool the hydrogen engine's exhaust, you'll be left mostly with nitrogen. So nitrogen is a feasible diluent that you can try. And some fuels, if you use some fuels like biogas and all that along with hydrogen, because they can also act as a fuel and they can also give some carbon dioxide. And this also could be used as a diluent. So we also tried carbon dioxide as a diluent. And the most sought after method for dilution is the recirculated exhaust, which is widely used in many engines. So that also has been tried. And the recirculated exhaust from an hydrogen engine will contain steam, because water vapor, and it will also contain nitrogen. So it is something which is in between these. So these three diluents were actually considered. Let us look at how the results show up when we have these diluents. Now, before we move ahead, we just look at the thermal efficiency versus equivalence ratio once again. I'm just trying to bring in the effect of equivalence ratio. So if you look at equivalence ratio, as I told you earlier, 1 means chemically correct amount of fuel and air. Anything less than 1 means more amount of air and less amount of fuel. So combustion can be complete, but fuel is less, fuel is lean. This is lean. So this is mostly lean mixture, which is what you will normally use in a hydrogen engine. So when we use a lean mixture in a hydrogen engine, as we keep on richening the mixture and going close to stoichiometric, the efficiency goes up. So if you lean down, the efficiency slightly drops. And this is because it is a general tendency of any engine. When you lean down, the power output drops. And if the power output drops, the friction dominates and then the efficiency drops. So it is not good to lean down significantly because the efficiency will drop. But this indicates the influence of leaning, what will happen. Now let us look at what will happen if you change the equivalence ratio and what will happen to nitrogen, the oxides of nitrogen. So this is fuel flow rate. So if I go to the left, fuel flow rate is reducing. That means mixture is becoming lean. Air is the same. You go to the right, fuel is increasing, air is the same, almost the same. And the oxides of nitrogen peak at around 0.8, equivalence ratio of 0.8. So leaning is always desirable. And if you lean below 0.5 or go close to 0.5, the NOx level is negligible. So if you want to operate a hydrogen engine, it is good to operate in a equivalence ratio range of about 0.4, 0.5. And if you are in this region, NOx is not at all a problem. Then there is no problem with the hydrogen engine as far as emissions are concerned. So it's a clean burning engine. But the only problem is that if you go here to 0.5, your thermal efficiency may be less as compared to what you will get here, and your power output will also be less. But this can be offset, which I am not going to show here, by supercharging or turbocharging. So throttling and always keeping the mixture at about 0.5 equivalence ratio. If it is too lean, you throttle and bring it to 0.5 and never go to this side. If you want to go to this side, the NOx will go up. And if you always stay around 0.5, you can get a reasonably high efficiency, which you can see here, and also get an extremely low level of NOx. This is one of the ways of attacking NOx in a hydrogen engine. But if you use diluents, then you can overcome this problem. Now, this is a setup we use to study the influence of diluents. And as I told you, the study of these diluents has some meaning practically. Like nitrogen is like cooled exhaust of the hydrogen engine. And EGR is what you can very easily get from a hydrogen engine. And we studied CO2 just because CO2 has a thermal effect, and we wanted to differentiate between thermal and dilution effects. So we studied all these three diluents. So the gases were allowed along with hydrogen. So you have hydrogen going through the flame arresters into the engine, and you also have either nitrogen or CO2 going into the intake manifold along with air, and the engine being studied as it was running. So you see here, first we are going to compare different methods of reducing NOx. The easiest method, as I told you, was retarding the spark. So we'll look at how effective spark can be to reduce oxides of nitrogen. Now this shows this is the spark timing versus oxides of nitrogen. So you can keep on retarding the spark and the oxides of nitrogen will keep on coming down. That means as you retard, the oxides of nitrogen are coming down. This is at a low fuel flow rate. This is at a high fuel flow rate. That means this is at low power, this is at high power. In both the conditions, retarding the spark is reducing the NOx levels. But what is very seen here is that at low loads, retarding the spark can bring down the NOx below 1000 ppm, below gasoline levels very easily. But at high loads, retarding the spark cannot bring down the oxides of nitrogen levels significantly. At high loads, by spark, it is not possible to control the hydrogen engine's NOx level. That is what this shows. Another thing which it shows is that even at low loads, if you want to retard the spark and bring down the NOx levels, let us say to 0 degrees before top dead center is the spark time, hydrogen, the NOx level would be something like 1000. If I come to 0 here for the low load application, the efficiency significantly drops. You can see here. So retarding the spark is not a very good way of controlling NOx in a hydrogen engine. And in the high load, retarding spark does not even control the NOx significantly. So this is not an option, which is normally carried out in the gasoline engine. This is not an option for the hydrogen engine because you are significantly not able to reduce the spark. So looking at other diluents, NOx controlled by nitrogen, this is got a practical application because it is like cooled exhaust of the hydrogen engine itself. Take the exhaust of the hydrogen engine, cool it, condense the water and circulate it back. Then it will contain not all the exhaust, some amount of exhaust circulated back. It will contain a significant amount of nitrogen. So this is dilution by nitrogen. So here what you see is the engine being run with a constant flow rate of hydrogen, constant flow rate of air, and only the nitrogen flow rate is changed. That means along with air, you allow some nitrogen. The amount of hydrogen is not varied. So the power output of the engine does not significantly change unless efficiency changes. The power input to the engine is more or less the same. And as we increase the amount of nitrogen, you see that there's a significant drop in oxides of nitrogen. This is NOx, significant drop. And at about a nitrogen flow rate of about 6 or 7, at 6 itself, you find that the oxides of nitrogen have dropped to about gasoline levels. And beyond that, they have dropped even below gasoline levels. And if you look at the same figure here, similar figure here with indicated power, up to the nitrogen flow rate of about 6 or 7, there is no significant drop in power. So we find that if you dilute the intake charge with nitrogen, which is equivalent to diluting it by recirculated exhaust, which is cooled, you find that you can control NOx significantly without sacrificing the power output or efficiency of the engine. So dilution by nitrogen is a good method of controlling the oxides of nitrogen in the case of a hydrogen engine. This is at high load. Now let us look at the other extreme case, which is low load. This is low load. Low amount of hydrogen. That means there is significant amount of oxygen in the cylinder. Small amount of hydrogen only is going. At that condition, you need significantly high levels of nitrogen to bring down the oxygen level. Then only the oxides of nitrogen fall. And even here, you find that there's no big change in the thermal efficiency. So bringing down nitric oxide using nitrogen dilution, that is cooled exhaust gas, is an option, viable option. It will bring down the oxides of nitrogen significantly. So this is what this entire thing shows. And the effect is not thermal, the effect is dilution. That is, the effect is one of concentration, reduction in the concentration of oxygen. Why I say this is, nitrogen specific heat is very close to the specific heat of air. So replacing air by nitrogen does not significantly alter the specific heat of the charge. So it is more of a dilution effect than a thermal effect. And you can see how the oxygen concentration has come down when we add nitrogen. So this is the full load which we saw. As we add nitrogen, the oxygen concentration has significantly come down. And the oxygen concentration in the charge is only about 1%. That is excess oxygen. That is the oxygen concentration in the exhaust actually. What is the excess oxygen? So if you can bring down the oxygen concentration to about only 1%, which is more than what is required, 1% in the exhaust, at all these 1%, you find that the NOx levels are very low. So if you can control the exhaust oxygen concentration to about 1% by sufficiently diluting with nitrogen or recirculated cold exhaust, nitric oxide can be controlled significantly. This is what this shows. So the hydrogen engine needs this sort of a process to control its oxides of nitrogen. And to boost power, you use supercharging. And we also see some additional things. That is, by changing the nitrogen flow rate, there is no need to significantly change the spark timing. Spark timing is more or less the same. So you can use the same spark timing. And we also see here that by using nitrogen, we don't significantly affect combustion. All the heat release rates are more or less the same, but different amounts of hydrogen, which is what is shown also in the efficiency. Efficiency does not change significantly as we go from here to here. So that's what it is showing. The reasons for that are clear here. The next diluent that was tried was carbon dioxide. And if you look at carbon dioxide, you find that if you replace nitrogen with carbon dioxide, and why carbon dioxide is used is just to study the influence of diluent, which has got more thermal effect. And why CO2? CO2 has a high specific heat. Particularly at high temperatures, the CO2 specific heat is significant. So it can be a suppressant and bring down the combustion temperatures. And if you bring down the combustion temperature also, NOx can come down. So you can see that if you keep on adding CO2 also, NOx comes down. But the downside is adding CO2 also brings down the power. So this is a method of control which is not desirable. And if you want to really bring down NOx to say 1000 ppm, you have to add 8 kg per hour of CO2 at full load. And at 8 kg per hour of CO2 at full load, there's a significant drop in efficiency. So CO2 dilution by CO2, though it can reduce NOx, it's not a very viable method. That's what we found through these experiments. So I don't go more into this. And let me go to exhaust gas. Now this is a viable method because you have exhaust coming out of the engine. You simply recirculate the exhaust, and the exhaust that comes out of a hydrogen engine contains water vapor, which itself can be a diluent, and it also contains nitrogen like what we saw. So both of them could be beneficial. And you can see here that again we did the experiments at different fuel flow rates. That means this is a high power output, lesser power, lesser power, lesser power, and lesser power. And the trend is very similar to what we saw with nitrogen because the predominant component in the exhaust is nitrogen. So by recirculating exhaust, which we didn't even cool, we're recirculating nitrogen plus steam, which is the exhaust, and we are able to significantly control oxides of nitrogen. So this is somewhere in between nitrogen and CO2. It doesn't also affect combustion significantly. All the combustion rates are very similar to what we saw with nitrogen. And the oxygen concentration also falls. And when it falls to this level, we find that the NOx is becoming negligible. So again, about 1%. When the oxygen concentration in the exhaust is about 1%, we find that there's a significant drop in nitrogen, in oxides of nitrogen. So EGR is a viable method of controlling oxides of nitrogen. It's a practical method, and nitrogen shows us the direction. Now, when we now went to a practical engine and see how it would actually perform, the amount of EGR that was required at different loads. This is low hydrogen flow rate, high hydrogen flow rate. That means low load, high load. The EGR that is required, the amount of exhaust that is to be recirculated, comes down as the load increases. And the loss in efficiency is only very small because of this circulating exhaust. If you want to control the oxides of nitrogen to about 1000 ppm, and the indicated power is also shown here, which is shown in this diagram. The indicated power obviously is going up as the load increases. So this is a viable method, practical method of controlling the oxides of nitrogen. That's what this shows. So I'll skip this. So now we saw how hydrogen can be used in the case of a spark ignition engine. I next want to show you how it can enhance the performance of low-grade fuels. How hydrogen can be used along with another fuel so that it can be its performance can be enhanced. Now what we see here is biogas. Biogas is a poor fuel, but it's almost available free. It is got from the anaerobic digestion of plant and animal matter, organic matter, and it contains about 60% methane, and the rest is mainly carbon dioxide. So it has a diluent, like what we studied there, which can bring down oxides of nitrogen, and it has also got a fuel, but this fuel is highly diluted with carbon dioxide. So normally in a biogas engine, you have problems of efficiency because of the low flame speed, narrow flammability limits, high octane number, high self-ignition temperature, and sometimes some hydrogen sulfide is present, and this gas is corrosive, but H2S can be removed. And CO2 also, if you take efforts, can be removed. So what we are trying to do here is improve the performance of biogas by using small amounts of hydrogen and studying how much of hydrogen is required to enhance the performance of biogas. You may be aware today that we use what is called as ethane. Ethane is natural gas with small amounts of hydrogen, and this hydrogen is supposed to enhance the performance of natural gas. This is something like that, biogas plus hydrogen. So problems with biogas, the carbon dioxide leads to low flame speed, poor efficiency, low energy content. The hydrogen sulfide leads to corrosion, but it can be removed. There's also water in biogas because the main formation of biogas itself is in the with a slurry, so that again can be removed. But this is the main problem which we are trying to address here: low flame speed and poor efficiency. Now this shows an experiment on a spark ignition engine where uh, different amounts of hydrogen were mixed with biogas. The main fuel is biogas. If I say hydrogen is 0, it is 100% biogas. Hydrogen is 5%, means 5% of the energy is coming from hydrogen, 95% is coming from biogas. So this shows the fraction, the percentage of energy that comes from hydrogen, and the remaining comes from biogas. And in all the cases, the spark timing has been adjusted for best efficiency. So what you see here is this black line. I'll only show the extremes. This black line is no hydrogen, that means only biogas. And this blue hydrogen line is the one with hydrogen, with 15% hydrogen, 10% hydrogen, and then you have 5% hydrogen. So you see that when you add hydrogen, the efficiency goes up, and this is mainly because of the improvement in the combustion rate. So the biogas starts burning faster because of hydrogen, and that improves the combustion rate and improves the efficiency. So a significant increase in efficiency. 5% increase or 4% increase in efficiency of an engine is significant because the engine's efficiency is, at this condition, let us say it was 20%, 20 or 22%, going from 22% to 25 or 26% is a significant benefit. So you see that there is a significant raise in the efficiency with lean mixtures, low equivalence ratio. Whereas if you go to high equivalence ratio, putting more hydrogen is not beneficial because it makes the combustion to become very fast. So putting less hydrogen is beneficial. So for example, this 5% hydrogen is maximum here, 15% hydrogen is maximum here. So one has to tune the amount of hydrogen that is mixed with biogas depending on what equivalence ratio is being used. And if one equivalence ratio is being used, you can always fix the hydrogen percentage. So there is an advantage with efficiency. The other significant advantage is with the emissions. Biogas being a poor fuel does not burn well. This is the black line is only biogas, and it leads to significant amount of hydrocarbon emissions. On the other hand, the moment you put hydrogen along with biogas, you find there's a significant drop in hydrocarbons. This is simply because the biogas burns more completely because of the higher temperatures which are reached in the combustion chamber due to combustion of hydrogen. So the faster combustion of hydrogen raises the temperature inside the combustion chamber, and all the biogas that would not have burnt earlier now completely burns. So this is what we see here. Significant drop in hydrocarbon levels when you have hydrogen being mixed with biogas. This is a big advantage because the hydrocarbon that comes out when biogas is burning is mainly methane. And you know, methane is also a greenhouse gas, which can be significantly cut down here. And it is not necessary that the nitric oxide level goes up because in biogas there's a lot of CO2. I told you that there's about 40% CO2 in biogas. So that itself acts as a diluent. And so you find that even with addition of hydrogen, the NOx emission is not going up. So this is another significant added benefit. You don't increase NOx, but you decrease the hydrocarbon emissions. You don't significantly affect combustion. You don't significantly affect NOx, but you significantly influence combustion process. The heat release rates are increased, but NOx is not increased because you still have a diluent which is CO2. So mixing hydrogen and biogas is a viable option again. Where it can be done in large stationary engines. You know that many community wastewater treatment plants and waste treatment plants use biogas generators. And these biogas generators are now feeding biogas engines, and power is being generated at some locations. And there it is easy to mix a small amount of hydrogen along with biogas and enhance the performance. So this is a viable option. And this shows, let me leave this. This shows that an engine where you mix hydrogen along with biogas becomes more stable than an engine which does not use hydrogen. This actually shows instability. The coefficient of variation of IMEP is how the IMEP of the engine or the torque of the engine fluctuates. Particularly when you make the mixture lean, the torque starts fluctuating. But when you put hydrogen, you can go leaner without the torque starting to get fluctuating. So hydrogen makes the engine to operate more stably. That is, more stable torque can be obtained when you mix hydrogen along with biogas. This also is another benefit. So this is one way of using hydrogen along with biogas. The other way is to go use what is called as a homogeneous charge compression ignition engine. Now, this is a new kind of engine where you take, it is unlike a diesel engine, unlike a petrol engine or a spark ignition engine. It uses a homogeneous mixture like a spark ignition engine, and it uses compression ignition like in a diesel engine. So it's something somewhere in between a spark ignition and a compression ignition engine. So the key factor here is a very lean mixture of air and fuel is taken during the suction stroke into the engine, and it is compressed. And at the end of compression, this lean mixture, and it's compressed significantly. So it is compressed significantly. Sometimes its temperature is raised and then it is compressed so that it auto ignites. That means self ignites at multiple points inside the combustion chamber, and the combustion rate is high, but the local temperatures are very low. Since the local temperatures are very low, you don't have significant levels of NOx, and you have ultra low levels of NOx. So this is an engine which can run with high efficiency, but with ultra low levels of NOx. But the problem is that when you compress, you do not know when combustion is going to occur. So control of combustion is very difficult. And the other problem is you have working only at low load ranges, not at high load ranges. But it is an upcoming method of combustion. So we have to see how this performs with hydrogen. So in a homogeneous charge compression ignition engine, or the so-called HCCI engine, you induct a homogeneous mixture of air and fuel. You may add some diluents along with this mixture to condition the charge. You may also change the temperature of this by heating the charge to raising it to some temperature. Then you compress this mixture of air, fuel, and additives after it is conditioned for its temperature. Then it self-ignites at multiple ignition centers, and combustion occurs at low temperatures, and you get low levels of NOx and almost negligible soot. This is what is the key, this is what is the advantage with the HCCI engine. Now let us look at a hydrogen-fueled HCCI engine. So this is one of the earliest works of hydrogen-fueled HCCI, which we did, and it showed that this has a promising, it's promising. So we wanted to actually conduct a feasibility study of using hydrogen HCCI engine because HCCI was becoming popular, and hydrogen cannot self-ignite so easily. So definitely the intake charge had to be heated, and the equivalence ratio had to be controlled. And we wanted to identify the limitations of this mode of combustion, and we wanted to see how we can extend the load range of this kind of combustion and compare it with conventional diesel operation. So this is the specification of the engine. It's a stationary single cylinder engine, but it is using hydrogen and air as the working medium. So again, you see that this is the engine. Hydrogen is supplied through a flame trap into the intake manifold, and carbon dioxide was used sometimes as a diluent, so that is shown here. And the exhaust emissions are measured, cylinder pressure and other important parameters are also monitored. So first we did, so we identified the temperature that was required at different hydrogen flow rates, and the second phase we tried to see whether adding some carbon dioxide extended the load range. And these were the two things which we'll see here. Now this experiment is a slightly involved experiment because hydrogen can very easily misfire or it can lead to knock. And we are also controlling the temperature of the charge. And the temperatures at which we controlled were all temperatures which we can normally reach in the engine because the exhaust which is coming out is hotter, is higher at a higher temperature than these. We can use the exhaust itself to create, to heat the intake charge. Now, if you look at this, let us say an intake temperature of 80 degrees Celsius, you can use high levels of hydrogen, equivalence ratio is high, and you can see all these equivalence ratios are much lower than what we saw earlier. That is because the HCCI engine operates with lean mixtures. So Low intake temperatures are used with high amounts of hydrogen. High intake temperatures like 130 degrees is used with low amounts of hydrogen, because if you use low amount of hydrogen with large amount of air, it doesn't get ignited unless you raise the temperature. If you use a relatively high amount of hydrogen with a relatively smaller amount of air, it gets easily ignited. But then relatively high amount of hydrogen leads to high power output, so high thermal efficiency and high power output. Low amount of hydrogen leads to low power output, which automatically is associated with low thermal efficiency. This is what we see here. So it only means that if you want to go from a low load to high load, you have to vary the temperature of the charge, and then you can go from low load to high load by gradually increasing the hydrogen. And at any given amount of hydrogen, having the lowest possible temperature, this is the lowest possible temperature. This is 130, this is 110. So at any given equivalence ratio, having the lowest possible temperature is the one which gives you the highest efficiency. So if you control the temperature properly of the intake charge, then you'll be able to go from a low load to a reasonably high load in the case of hydrogen, and get reasonably high efficiencies. And these efficiencies are higher than the normal diesel engine. Diesel engine in itself is a highly efficient engine. And with hydrogen HCCI, it is possible to reach efficiencies which are higher than the diesel engine. This is what this indicates. And the other advantage is the oxides of nitrogen. The oxides of nitrogen are extremely low with the HCCI engine, hydrogen HCCI engine. The diesel engine's NOx could not be shown here because it is much above this. It will be somewhere around 6 to 7, whereas this is less than 0.5. So you can see that there's a significant drop in the NOx level. No smoke at all because there's no diesel, and high efficiency. So the hydrogen HCCI operation has potential to operate with high efficiency, low NOx, and almost negligible other emissions of other pollutants. And only thing is, with the hydrogen fluoride, the temperatures have to be controlled. And the other main disadvantage is that the BMP range is limited. And if you want to extend this, you have to supercharge the engine. Then you can extend this BMP range. But it shows this direction that hydrogen HCCI can reduce oxides and NOx and also work efficiently. And how this happens is like this. If the intake charge temperature is very high, combustion occurs even before the piston reaches top dead center. 360 is top dead center. Combustion occurs before the top dead center, so efficiency is bad. But if you put the right temperature, for example, this green line, combustion occurs at the right region, that is slightly after top dead center, and it is almost instantaneously completed, and you find that the efficiency is also high. This shows the heat release rate, how reducing the temperature can retard the combustion and also bring down the combustion rate to reasonable levels and achieve hydrogen compression ignition. So this is what it shows. And one way to retard the combustion process is also to use diluent. Here you see no carbon dioxide, small amount of carbon dioxide, high amount of carbon dioxide. The combustion is retarded, and what was combustion which occurred very early has now been pushed to the right point to get high efficiency. So it is possible to extend the load range to go to higher BMEPs as compared to what we saw earlier by adding a diluent and then raising the amount of hydrogen that can be used. In fact, we could progressively add diluent, raise the hydrogen quantity, diluent, raise the quantity, and go up to this point, which was something like 3 bar of BMEP, which was significant, 3 to 3.5 bar of BMEP, which was significantly as compared to what was reached earlier. So by using a diluent and also by controlling the temperature of the intake charge, a hydrogen HCCI engine can be operated at slightly higher loads and much higher loads by supercharging with negligible oxides of nitrogen levels. This is what this work shows. And this shows the efficiency of the engine when there was no diluent, blue line, and there was this diluent, this brown line. So you can jump. And we also compared our work with what others were doing, and we could, for example, this is the literature that was available at that time. They went only up to a IMEP of 2.2 bar, whereas we could go to almost double that IMEP. And we could also go to higher efficiencies than what was achieved at that time. So it is possible to run a hydrogen HCCI engine with proper control measures, with low NOx levels and very good efficiency, And provided we turbocharge it, we can also boost the power output of the engine. This is what it shows. And when we compare hydrogen operation with diesel, this shows how it compares. This is at a low output. All these are relatively low outputs, which are reached by HCCI. You can see always the hydrogen HCCI mode is more efficient than the diesel mode, CI mode, and oxides of nitrogen are just negligible. Diesel's oxides of nitrogen is here, and hydrogen oxides of nitrogen is somewhere here. So negligible oxides of nitrogen, higher efficiency is what the hydrogen HCCI mode brings. So I wish to now summarize and conclude because we are nearing the time. So the hydrogen HCCI, hydrogen SI engine can operate up to a maximum about 80% of a gasoline engine's output. But if you supercharge, you can cross that output. And the brake thermal efficiency is higher than gasoline. And the equivalence ratio range is about 0.3 to 1 for the hydrogen engine, whereas it is wider for the gasoline engine because it will not knock so easily. And the emissions with HC are negligible. The NOx levels are very, very high in the hydrogen engine, but can be controlled with the use of diluents like nitrogen and by properly adjusting the spark timing. So this is what we see in the hydrogen SI engine. And hydrogen can be used to enhance the performance of poor fuels like biogas, which have low efficiency and high HC emissions. Using small amounts of hydrogen, you can significantly bring down the HC and also raise the efficiency. And NOx levels do not go up, and engine becomes more stable. And about 10% of energy from hydrogen is enough. And this can be used for stationary applications. Hydrogen HCCA operation is feasible in a equivalence ratio range of 0.19 to 0.3. Efficiencies are much higher than diesel. Then you have high thermal efficiency, low emissions, extremely low levels of NOx that are not definitely possible in any other mode of engine operation. And proper control of combustion facing by altering the temperature and use of diluents is required to extend the load range. So this is what we see with hydrogen. So hydrogen is a promising fuel, but there are many questions to be answered in hydrogen: how to produce hydrogen, how to store hydrogen, how to transport hydrogen. These are all issues which have to be solved before hydrogen can be widely employed. But for stationary applications and for places where hydrogen is available as a byproduct of some industry, it is definitely a viable fuel to be initially used. And unless hydrogen is produced from a renewable source, it doesn't make much sense to use hydrogen, because if you are using electricity to produce hydrogen and that electricity comes from coal, then it does not really serve the purpose, because anyway you will be emitting CO2. So hydrogen use is something like electricity use. So one has to very carefully think about how it can be used. And production of hydrogen is one of the key things to be addressed before hydrogen can be put to wide use, because its source is very important. And hydrogen is always thought as a energy carrier. So you have electricity, surplus electricity, you can produce hydrogen and store it, and then use hydrogen as a fuel. So it's a sort of a energy carrier. Of course, there's another way of using hydrogen, that is the fuel cell, which I have not dealt with. And I wish to acknowledge the support from the following: Mallikarjuna Purpadam, Dr. Purpadam, and Dr. Subramaniam, and Dr. Ibrahim, so who all helped us in doing all these experiments. Thank you. Any questions, I'll be happy to answer.
Thank you, sir. Any questions from the participants? Please unmute and raise your query.
Hello, sir. Myself, Dr. D.B. Jani speaking.
Yes, please.
Want to know, one of the major challenge for the hydrogen is about its storage volume. Okay. So is
Yes.
there any latest innovation with regarding to have a better storage facilities available for the hydrogen?
Actually, what people are trying is, see, there are two methods of storing hydrogen, as you will be knowing. One is to store it as a compressed gas, which is very common, and the other one is to store in a metal hydride, as a metal in a metal hydride. So the metal hydride storage facility is bulky but very safe. It has a high mass. That is, the storage efficiency is not very high. But the compressed gas storage is better, but it is not so safe because you are storing it under pressure. And today people have raised the storage pressure from, I think, now they've gone even up to about 600 bar, and they are thinking of even higher pressures. So once you go to such pressures, you can store a reasonable amount of hydrogen in a reasonable volume. But if you are storing at 200 bar and all that, it is definitely not the way to use it for transportation. But if you look at a stationary application, then hydrogen is okay because you don't have to really store and the volume is not a problem. So as of now, the storage is basically with compressed gas, using cylinders with different materials, composite cylinders, and so on.
Okay, thank you, sir.
Hello.
Hello.
Good evening, sir. Thank you. Thanks for this wonderful lecture, sir. Sir, I have one query, that is, how viable is the widespread adoption of hydrogen as a primary fuel, considering the current state of infrastructure for production, storage, and distribution?
I considering the current status of production, storage, and distribution, I don't think hydrogen is immediately applicable. In fact, if I just have to go back and see, even in the time in which I have been working for the last, let us say, nearly 30 years, hydrogen has come and gone once. And even before that, it came and went once. So hydrogen, the main thing is that the hydrogen usage technologies are being developed, like the engine, fuel cell, and all that. But the problem is in the availability of hydrogen. So unless hydrogen is available from green sources widely at economical, which are also economical, and it is also possible for us to store properly and transport it, it will not find wide use. But I'm sure people are working in this direction, and I don't think the present level is anything which will allow it to be widely used. We still have to go further. This is the present state. But what is happening is we develop technologies to be ready when hydrogen comes. But definitely there's a lot of improvement as compared to what was there earlier, because now we have come to composite cylinders. Now we have got a lot of renewable electricity. So once these things increase, then maybe hydrogen becomes more viable. Because hydrogen requires electricity as of now, because it is mostly electrolysis. It requires clean water because electrolysis again is from water, so clean water, and it needs to be transported. These are three main things. Hello?
So thank you very much, sir.
Good evening, sir.
Good evening.
Sir, first of all, I would like to thank you for this wonderful lecture, sir.
Yes, please. Thank you.
So my small query is, sir, can we use the oxy-hydrogen gas for the onboard application, sir?
Oxy-hydrogen, you
Yes.
know, if you use oxy-hydrogen, yes. Oxy-hydrogen, you're saying that you will not use air, is it? No air, only oxygen and hydrogen. The only problem with such things is, yes, it can be used. Only problem is you will have high levels of high temperatures, very high temperatures, and unless there is something to suppress these temperatures or materials which can withstand these temperatures, it's going to be difficult. Because the temperatures that you will reach, see, when you burn along with air, nitrogen is the diluent. So nitrogen suppresses the temperature. But now when you don't have this nitrogen, you need to suppress these temperatures. You may have to use the recirculated water and all these things. Otherwise, temperatures will be very high. So I don't think it is directly feasible. But what may be feasible is use of a small amount of oxygen. See, you have, when you produce hydrogen, you may be producing oxygen, and use of that oxygen elsewhere, in my opinion, may be feasible.
Okay, sir. Okay, sir.
along with the same hydrogen.
Okay, sir. Thank you, sir.
Sir, namaste,
Sir,
sir.
if possible, can we see you, sir? Please, I mean, we are unable to see
Actually, there
you.
is some problem. I don't know. My camera is on.
Okay, okay, sir.
I don't know why it is
Okay,
not
sir.
coming.
Thank you so much, sir. Thank you, sir.
Yeah. I don't know why it is not coming. Actually, my camera is on, but there is some
Okay,
problem.
sir.
I'll just try to.
Okay, sir.
Sir, good evening, sir.
Good evening, please.
Thank you, sir.
Myself, Dr. V. Suresh, sir, from Godavari Institute of Engineering and Technology, Rajahmundry, sir.
Okay.
Sir,
Please
sir,
tell me.
I have a doubt, sir. For integrating the renewable energy sources like solar and wind to produce the green hydrogen, sir, what are the main challenges or what are the main things to consider to produce the green hydrogen?
Actually, I am not so competent to talk about hydrogen production. But to produce green hydrogen means you need electricity which is green.
Yes, sir.
That is the main challenge. So you need electricity which is coming from renewable sources like hydel or solar or whatever, wind. And unless we have such electricity, I don't think we will be able to produce green hydrogen immediately. Because it is limited by that. And this hydrogen, in my opinion, hydrogen and electrification have similar constraints.
Yes, sir. Yes, sir. Sir, in
Hydrogen
future,
has both have problems with production, and
yes,
one
sir.
has problem with storage, one has production problem with battery disposal. So these are the issues which have to be solved, and they are real issues, no doubt about it. But
Yes,
for
sir.
stationary applications, the storage problem of hydrogen at least can be eliminated.
Okay, sir. Okay, sir.
So hydrogen has to be looked at, in my opinion, in the near future, it should be looked as an energy carrier.
Yes, sir. For all transportation applications, this is the fuel for future.
Yes, but that's what. But we don't know how things will go
Yes, sir.
because there are so many things linked to it.
Actually, I have an idea, sir, to develop to produce hydrogen storage from renewable energy sources. Like that, I have so many challenges. How can you develop and what are the things to consider for implementation?
The main
Like,
problem is production only.
sir.
And one more problem thing is that if you want to produce from by electrolysis, you also need clean water.
Yes, sir.
And water also is a scarce commodity now.
Yes, sir.
So all these challenges have to be tackled.
Yes, sir. So, thank you, sir.
Good evening, sir. One
evening.
participant raised a question in chat box, sir. I will read. What is the significance of reduced throttling for hydrogen?
Actually, hydrogen works very well when the equivalence ratio is close to about 0.5, 0.4, 0.5. So if you are using very little hydrogen and you are not throttling, then you may go to equivalence ratios which are something like 0.2, 0.3 and all that, which will not be very good for efficiency. And under those conditions, it will be useful to throttle. Or you can even avoid the throttle and do what is called as variable valve timing to take less air. So it will be advantageous at part load conditions. Because otherwise it will become too lean. And if it is too lean, the efficiency drops. If it is richer than 0.5 also, NOx goes up. So you have to be close to 0.5. So it is good to throttle sometimes and bring it close to 0.5. Did I answer the question?
Hello, Ramesh sir.
Yes, please.
Very good evening, sir. I am Dr. K. Bala Prasad from RVR and JC College of Engineering, Guntur.
Yes, please.
So I heard your excellent lecture on the hydrogen generation, sir. And I heard that you have been experienced in this field by around 30 years.
In engines, hydrogen maybe around 15 years, but in engines, I've been working on engines for 30 years. Yes. Yes, please.
How many years it takes to have our vehicles with hydrogen on the road, sir?
Sorry. How many years?
Hello, sir.
I didn't hear your last question.
Yes, sir.
I didn't hear your last question properly. Can you please repeat it?
In your point of view, how many years it may take to have the vehicles run on the road with hydrogen and the fuel, sir?
Running on the road, see, running on the road has many constraints.
Actually,
First of all, you are asking me how many years it will take to see hydrogen vehicles on the road. Is that a question?
hello?
Are you? Is your question how many years it will take to see hydrogen vehicles on the road?
Hello, sir.
Hello, am I audible? Hello.
Yes, sir, you are audible, sir.
I think he is not able to hear me. I think.
Yes, sir, yes, sir. That is the question raised by the Balaprasad, sir, sir.
Yes, yes. So I mean, I'll give the answer, but I don't
Your
know.
voice is audible, sir.
Okay. I think he is not able to hear.
Yes, sir, yes.
Hello, sir.
Yes, please.
With your knowledge of expertise, how many years it may take to run the vehicles on the road with hydrogen as the fuel, sir? In your point of view?
In my point of view, it'll take quite some time. I don't see it in the near future.
Oh.
The reason is that first hydrogen should be available at such scales and it should be distributed. It may come in certain countries. See, for example, Germany has got a good is coming up with some distribution systems, but even there, I don't think it will be widely used because there are so many questions. One is availability, distribution, storage. All these have to be, and safety. So all these have to be met. So I think it will take quite an amount of time.
Okay. Thank you.
But if you are using small quantities of hydrogen, like hydrogen, ethane, and all that, that you will see, and we are already seeing it.
Okay,
So
thank
I
you,
think
sir.
initially it may be mixed with in small quantities with other fuels and used, like natural gas, and so on.
Okay, thank you, sir.
Hello.
Sir.
Hello.
Sir,
Hello?
if no questions, I have one request, sir. All the participants, please switch on your videos for a snapshot.
I don't know. My video is not coming. I have switched on. I don't know what is the reason. Huh?
Sir, I have a small doubt, sir. As we are facing many difficulties with hydrogen from production to carrying it and running the IC engines with hydrogen, but why the government is stressing to produce more
No,
and is stressing on more
see,
production of hydrogen, sir?
no. That is the way to go. But right now we are in this position. That's all. It doesn't mean that we'll not be able to go there. See, unless we make an attempt, we'll not go there. So, what I'm saying is that I'm not saying it is impossible to go there. I'm saying that it will take some time to go there, but we should be making efforts. No, all over the world they are making efforts. So, and the application may not be immediately on cars. It may be in places where it can be easily stored. For example, in a ship or a train, where you can easily store. You may first use it, and then slowly it will come. And we are not looking at the immediate future. It will come, but unless we make an attempt, it will not come. And it is a viable. It is a good fuel, and we should make it viable. That is what is happening now.
Okay, sir. Thank you.
Dear participants, switch on your videos for 30 seconds. All of you, please. Mallikarjuna, sir.
తీసుకున్నారా
Hello? Andras, sir.
Sir, already taken, sir. Screenshots are taken.
Okay, thank you. So thank you very much, sir, Ramesh, sir. By sparing your valuable time, you have delivered a nice talk to the participants. Definitely, some of the participants may be inclined to take research in this area, sir. Hydrogen fuel IC engines. Thank you so much, sir, for giving a nice talk.
Thank you very much for staying this long and patiently hearing. It's not so easy at 9:30. Thank you very much. Thanks to all the participants, and all the best to all the participants in the research.
Thank you, sir.
Participants, there is one important announcement. Three things are very, very important here. 80% of attendance, first one. Second one is scoring of 70% marks in the exam, which is to be conducted on day 6. That is the last day of the FDP. Third one is of your feedback on day 6. These are very important to get a certificate from AICTE. Okay, keep in mind. And also, all of you, please join with your unique ID that was provided to your mail.